Hey, morning, folks. All right, here we go. Kind of last week, Unit 9 for us. So day 6, notes for us. Oof. All right, so today we're going to talk rotational kinetic energy. Now, notice the video on the right. I just took a screenshot of kind of the intro screen of it. I would recommend checking this video out. It's not super long. You can see it's 3 minutes worth of your time. But and I even skipped ahead to like minute 1.5 or minute 2. Just to see the actual real world application of a ring and a disc. But the gentleman does a nice job of talking about it. I'll warn you, it's probably some of the best 1990s cinematography out there. Okay, so here we go. All right, so when we look at this one now, what we're going to see here is this is the formula for us. All right, so kinetic energy in the rotational kind of realm, so to speak, is equal to 1/2 I omega squared. Again, kinetic energy, that's still joules. It's still energy. It's still the ability to do work. All right. I is our moment of inertia. Remember resistance to rotation. That's going to be kilogram meter squared. And then omega is our angular velocity still in radians per second. Okay. All right. So let's check out a practice problem quick and then we'll talk conceptually about it. So the moon has a radius of 1.74 times 10 to the 6th meters and a mass of 7.23 times 10 to the 22nd kilograms. It makes one revolution every 27.3 days. All right. Determine the angular velocity, determine the moment of inertia. There's the sphere's formula. Again, you don't have to memorize that. That would be given to you. And then what is the kinetic energy of the moon? Now, if you want to go ahead and try this out, pause the video, go on and go ahead and try it out. All right. So here's what I got. So I listed my variables that I know. I got my radius of that, my mass of that, the theta, the angular displacement of it is one revolution, and the time it takes for that to happen is 27.3 days. All right. So for part A, it says determine the angular velocity. Remember, for this part, that's going to be the displacement over the time, distance divided by time. Well, this takes one revolution, which is 2 pi radians, over 27.3 days. Well, 27.3 times 24 times 60 times 60 times 24 to get it to hours, times 60 to get it to minutes, times 60 to get it to seconds. That gives me about 2.4 million seconds. All right. So 2 pi divided by that is 2.66 times 10 to the negative 6 radians per second. It's not moving very fast, at least in our mind. Look at that. All right. So pretty standard kind of calculation for us. Hopefully that makes sense. All right. Part B, the moment of inertia. Now, remember, moment of inertia, resistance to rotation for a planet, this should be huge. Not only is the radius large, but the mass is absolutely ginormous. All right. So when we look at this one, we're going to use that 2/5 mr squared. All right. So we take our 2/5 times the mass, which is 7.23 times 10 to the 22nd kilograms, and then we square our distance. All right. What we end up seeing here is that we get 8.76 times 10 to the 34th kilogram meter squared. Now, is that an absolutely maniacally huge moment of inertia? Yes. I wonder what Jupiter's would be, just because that's the biggest planet that we have in our solar system. And that would be interesting to see. Maybe we'll find that out some other time. All right. So once we know those two pieces, then I just put them back over here, as you can see. So let me get my laser pointer. So there's my omega, right? That's how fast it's spinning. There's my moment of inertia, how much it wants to resist that movement. So then we plug it in for our kinetic energy. All right. So it's going to be 1/2 the moment of inertia, which is I, times the angular momentum squared, or angular speed squared, sorry. So we take 8.76 times 2.66 times 10 to the negative 6 squared, and it requires this much energy. So that's how much rotational energy it has, 3.09 times 10 to the 23rd joules. All right. Again, is that a huge amount? Absolutely. We're talking about a planet. Well, not a planet, but a huge rock that we're trying to get to rotate and do stuff like that. Yeah. All right. Then under the concepts. All right. So here we go. All right. Ready? So we got a frictionless cube slides down an incline. Well, the following roll down an incline. We got a solid cylinder, a shell of a cylinder, basically a hoop, right? A solid sphere, and then a spherical shell. So think of an empty sphere. All right. So now notice the delineation here. This part here for this frictionless cube, all frictionless, okay? So we then ask, okay, which one's going to be the fastest? Well, the fastest should be the frictionless cube, right? The reason is because it doesn't have to change any energy, meaning the energy goes from gravitational potential energy directly into kinetic energy. So it has to slide. It's not going to roll down the hill, right? So we don't have to transfer any energy into rotational energy like the rest are going to do. Oh, it's 15 minutes after. I love it. That's the quirks of the house. So what we're going to see then is that because that's going to slide, it really has no energy loss through conservation of energy, right? So for us, the other four, though, are going to experience rotational kinetic energy, right? So some of the GPE will be turned into rotational energy for those other four. This means there's less energy to be turned into kinetic energy, all right? What happens is that we lose some of, or we change some of that energy into causing them to spin, right? We have to overcome the concept of the moment of inertia. Now, if we want to talk about the fastest at the bottom, well, that's just our omega, right? That's just the big W. How fast we're there. So we know that GPE from based on that height is going to completely turn into kinetic energy here. Yes, we may lose a little bit of friction, but we're not going to say that that's a marginal amount. Okay? So what ends up happening is that that moment of inertia becomes incredibly crucial. Which one has the highest moment of inertia? So, like we say here, different moments of inertia will make the object roll at different rate. Remember, again, the moment of inertia is that concept of the resistance to rotation. So if all of these cylinders and spheres are the same radius and the same mass, we'll say, then really it just becomes about that moment of inertia formula. Because the moment of inertia is part of the kinetic energy rotational formula concept, this will play a role in which one obtains the highest speed. Because remember, if we talk about these all having the same mass and radius, then the GPE turning into KE is going to be the same for all of them, right? So based on that formula, we know that I becomes the determining factor. The moment of inertia does, all right? So if we look, the cylinder shell, the blue piece right here, right? It's got a moment of inertia of mr squared, okay? The spherical shell, that's this top one, the green one here, is going to be 2/3 mr squared, all right? The solid sphere is going to be 1/2 mr squared, all right? And then the solid cylinder right here is going to be 2/5 mr squared. So what you're starting to see is that the difference in the moment of inertia for these is the fractional component that we put up front of it, right? Once we know the fractional component of it, what we can start to do is we can start to see what changes, which one's going to be faster, so to speak, as we hit the bottom, right? So a couple questions before that. Which is more difficult to rotate? An object with a mass close to the axis of rotation or an object that has a mass far away from the axis of rotation? Or if we're talking about a moment of inertia, it's mr squared. So the one that should be more difficult is the object that's farther out. So that's where we see that shell, whether it's the cylindrical shell or the spherical shell, all of that weight is pushed out, right? So it's all out on the edge of that whole entire nebulous structure, okay? So which object has a larger moment of inertia? A solid disk or a hoop? Again, when we're talking about this larger moment of inertia, we are talking, okay, this solid cylinder here or this cylindrical shell right there, right? Remember, a hoop is I equals mr squared. A solid cylinder is 1/2 mr squared. Because the mass is closer to the center here, what ends up happening is the hoop should have the higher moment of inertia. Again, if they have the same mass and same radius, all right? So then, which object will take more time to roll down an inclined plane? So again, when we look at this, assuming that we have the same amount of mass and same amount of radius, the one with a higher moment of inertia, because the kinetic energy is going to be the same for both of those two, what we should end up seeing is a hoop is going to be the slower one of this, right? So which one will take the most time to get down the plane? Well, if we remember back to it, right? Our moment of inertia for this, the one that had the largest moment of inertia was that cylindrical shell. If our mass and radius is all the same, right, it was just mr squared. It wasn't half mr squared or 2/3 mr squared or 2/5 mr squared like the other ones were. So in that case, our cylindrical shell, right, the hoop should be the slowest, right? Then, which will take the least amount of time? I have a trick question here. The one that should take the least amount of time is your frictionless cube. All right. Reason being, it's just going to slide. It doesn't have to worry about transferring any of that energy into rotation. It is just going to take that GPE and turn it directly into KE. Right? Let me know if you got questions. Likely this will be more of a conceptual question on our quiz, or on our test, sorry, of like, hey, which is the fastest, which is the slowest of these couple here. Okay. All right. Have an absolutely fabulous day. I will try and get Section 5 answer keys whipped up. I will also try and get some practice for us on that as well. Okay. All right, folks. Have a phenomenal day. We'll talk to you later. Okay.